Now, coming to the entrance part of chemical bonding. Today I'll tell you some informations which I have not given in your regular classes, rather which is not there in your regular classes, which is there in your entrance part. Little bit, small informations I am going to give it to you. We are going to solve some questions also, so that I hope you will be liking this particular one. You will be also knowing a lot of thing about many of the compounds, many of the concepts of chemical bonding, little bit more, so to say, I'll be telling you. Now here FeCl3, you know that, has a greater covalent character than FeCl2. Alright, the reason is, this is because Fe3 plus ion has greater charges and smaller size than Fe2 plus. Definitely, by losing electrons, 3 electrons, the size of the Fe3 plus is smaller than the size of the Fe2 plus. The charge is also greater. Remember that when the charge is bigger, got it, the size is smaller, then definitely the electronegativity is also more. Got it? So hence, as a result, Fe3 plus ion has got high polarizing power than Fe2 plus. As electronegativity will be more, the Fe3 plus ion will be having high polarizing power than Fe2 plus. Now, how do we come to know? From the Fajans rule. Smaller size of cation, large size of anion. Alright, we come to know from the Fajans rule. From there we come to know. You may ask, from how do we know that? So in this way, remember that Fe ferric chloride is having greater covalent character than ferrous chloride due to this particular reason. Ferric chloride has got greater covalent character than ferrous chloride, FeCl2, we can say that. This is one thing, that is, let me tell you. Now next is that the solubility of aluminium halides. Alright, the solubility of aluminium halides means aluminium chloride, aluminium bromide, aluminium iodide, aluminium fluoride. It follows this particular order, that is AlF3 is greater than AlCl3 is greater than AlBr3 greater than AlI3. Alright, it follows this particular order. Clear? So this is because the size of the anion increases. Alright, it gets more and more easily polarized. Size of the anion is increasing. See, FCl, Br, the size is increasing, isn't it? The size of the anion, it becomes more and more. So hence it gets more easily polarized, and hence covalent character of the molecule also increases. Same thing according to Fajans rule. We can say that. So as the size of the ion increases, the size of the anion increases. Anion, you can say that the size of the anion is increasing, because fluorine, chlorine, bromine, iodine, down the group if I come, the size of the anion increases. So covalent character also increases. So hence we can say that solubility of aluminium fluoride is more than that of aluminium chloride, is more than that of aluminium bromide, which is more than that of aluminium iodide. We can say that. Clear? Now next point is that you may write this one point wise. Got it? It will be easy for you if you write it in point wise. The maximum number of covalent bonds formed between two atoms is never greater than 3. Alright, it's never greater than 3. For example, carbon we have this only, nitrogen we have this only. We cannot have any particular molecule whose what you can say bond is greater than 3. It is not possible. We can say that the maximum number of covalent bonds which is participating, because you know that Bohr's atomic radius 0.529 angstrom. So we cannot bring it closer to that, because as the bond length increases, as the number of bonds increases, the bond multiplicity increases. As the number of bond multiplicity increases, means single bond to double bond to triple bond, the bond length decreases. Now you cannot bring it more closer to 0.529 angstrom. That is not possible. Why? Because internuclear repulsion will be there. So hence, maximum number of bond is 3 only. We can say that. Clear? I hope you understood this. Now, a pi bond never formed alone. It is always formed with sigma bond. First a sigma bond is formed, then a pi bond is formed. Always remember that. First head-on overlapping takes place, then lateral overlapping takes place. This I have studied in a regular class also. Now, each atom always forms only one sigma bond in the covalent compounds. Definitely. Each atom never forms two sigma bonds. Each atom forms only one sigma bond. Why? Because hydrogen atom is having one electron. No? So it is going to form one sigma bond only. How it will form two sigma bonds? So hydrogen atom is always forming one sigma bond, got it, in its molecule. Now, next is for molecules or ions having regular geometry. Got it. The next point, the molecules or ions having regular geometry, the change in the electronegativity of the central what you can say atom or the surrounding atom has no effect on the bond angle. Alright, it has no effect on the bond angle. What I said, that for the molecules have, or the ions, the molecules or the ions have a regular geometry. Mind it, regular geometry, not distorted, regular geometry. Alright, the change in the electronegativity of the central atom or the surrounding atom has no effect on the bond angle. Example, that is, we can say BF3, BCl3, BBr3, BF3, BCl3, BBr3. You can see I am changing the surrounding angle. Got it? Bi3, I am changing the surrounding angle, but there is no effect on the bond angle. The bond angle remains the same, we can say that. There is no effect. Alright, all have the same bond angle. How much it is? You can say that BCl3 is how much? It is nothing but sp2 hybridized. BCl3s. Alright, AB3 type of molecule, BCl3s. Clear? BCl3. This is your BCl3. What is the bond angle? It is nothing but 120 degree. That is BCl3. So same thing, BCl3, BF3, BBr3, BI3. All they will have a bond angle of 120 degree only. We can say that 120 degree. Similarly, CH4, CCl4, NH4 plus, etc. All they have a bond angle of 109.5 degree. Alright, CH4, NH4 plus, and what you can say CCl4. What you find it here? That is, I am changing the central atom as well as I am changing the surrounding atom here. What is that? CH4, CCl4. The surrounding atom is changing here. Here the surrounding atom is changing, as well as NH4 plus. Central atom is also changing, nitrogen. From carbon it comes nitrogen. So when the central atom, surrounding atom, everything is changed. Alright, for regular geometry, mind it. Clear? Then what I said you, there is no effect on the bond angles. Clear? Fine. So in this way, this is another point I said you. Next is the bond angles may vary due to some other factors also. There are some other factors also by which the bond angle varies. Alright, that is a bond angle of ammonia. Listen carefully this one. Bond angle of ammonia is greater than that of NF3. Is greater than that of NF3. The bond angle of ammonia means NH3 bond angle is greater than that of NF3. Generally, NH3 bond angle is 107.5 degree, so to say, 107.5 degree. And NF3, the bond angle is 102 around 5 degree or 4 degree, we can say that. 102.4 degree or around 5 degree, 102.5 degree, also we can say that. So, again I repeat, NH3 is 107.5 degree and here it is 102.5 degree or 102.4 degree. So, the bond angle is varying. Why? What is the reason behind it? What is the reason? See here. Let us draw the structure, then we will come to know. Now, NH3 and NF3, what you find is that they are both pyramidal in nature. We can say that. Both are pyramidal in shape. So, that is, let us first draw NH3. We can say that. Alright, let us first draw NH3, but the bond angle is 107.5 degree. This is a lone pair. It is pyramidal. You can see that. Now, this is your NF3, where the bond angle is 102.4 or 102.5 degree. Here also we have got the lone pair, we can say that. Now why the bond angle is varying? Both are pyramidal in nature. Alright, so both have lone pair on the nitrogen atom, we can say that. See, as fluorine has higher electronegativity than hydrogen. Definitely, fluorine is having more electronegativity than hydrogen. This is hydrogen, okay? Yeah. So fluorine has more electronegativity than hydrogen. So the electron pair is attracted more towards F in NF3. Now, if you see, here it is from fluorine to nitrogen, the dipole moment is from fluorine to nitrogen. And here it is from nitrogen to hydrogen, the dipole moment is. Alright, clear? Here it is from nitrogen to hydrogen, so to say. So, the electron pair is attracted towards F as fluorine is having more electronegativity than hydrogen, we can say that. So, electron pair is attracted more towards F in NF3. Alright, that is a bond pairs of electrons are away from nitrogen, or in other words, that is the distance between the bond pairs, what you can say is that is more. Is away from nitrogen means the distance between the bond pairs is more. So as the distance between the bond pairs is more, the repulsion between the bond pairs in NF3 is less than that of NH3. As the distance between the bond pairs is more. So repulsion is what? It will be less. For that purpose, what you can find is that is, again I repeat, the bond pairs of electrons away, they are away from nitrogen. So, or in other words, we can say that the distance between the bond pairs is more. As a result, the repulsion between the bond pairs in NF3 Got it? In NF3 is less than that in ammonia, that is in NH3. Now, due to greater repulsions between the bond pairs in ammonia, got it? Greater repulsions a bond pair in ammonia. See, the bond pair repulses more here. Here the bond pair repulses less because fluorine is more electronegative than hydrogen. So the repulsion is more in ammonia. So due to the greater repulsion between the bond pairs in ammonia than in what you can see in NF3, so the bond angle in NH3 is greater than that of NF3. Is greater than that of NF3. We can say that the bond angle in ammonia is greater than that in what you can say NF3. So to say. Now, next is we will see another one, that is we will see PH3 and PF3. Alright, PH3 and PF3. Let us say this is your PH3, this particular one is PH3, and we will see another one, that is your PF3. We will see it. Clear? So here that is phosphorus, same thing, belongs to the same group as in nitrogen. Phosphorus, it's also having a lone pair of electrons present in it. Now, one more thing I will tell you here, that is what you find is that in PF3, one of the bond is a double bond due to resonance. One of the bond is double bond due to resonance. Here, fluorine is having 3 lone pairs. Here, fluorine is having 2 lone pairs. We can say that. Clear? So, here due to resonance, listen carefully here, that is what you find is that PF3 has a greater bond angle. PF3 has got a greater bond angle than PH3. It is just opposite to NH3 and NF3. In NH3 was having greater bond angle than NF3. Here PF3 is having greater bond angle than PH3. Alright, now why? What is the reason? This is due to resonance in PF3 leading to double bond character. Resonance in PF3 which leads to double bond character. As a result, repulsion between the PF bonds are large. The repulsion between the PF bonds is large and hence the bond angle is also large. So there is no possibility for the formation of double bond in PH3. In PH3 there is no possibility because hydrogen is having 1 electron only. So 1 electron from phosphorus and 1 electron from hydrogen they share, and we are having a single bond. So there is no possibility of forming a double bond here, but there is possibility of forming a double bond in PF3. Due to resonance, what will happen? You will find a double bond here. Then you will find another canonical structure here, double bond. In another canonical structure, you will find a double bond here. It is going to rotate, isn't it? You will have a different canonical structure. And as the number of canonical structure increases, the stability also increases. Because canonical structure increases means we are losing energy. The molecule is losing energy. So as the molecule loses energy, because energy is distributed, I told you in resonance. The more the number of canonical structure means energy is more it is distributed, and more the amount of energy is distributed, less energy is there in the compound, and less energy is there in the compound means compound is more stable in nature. Alright. So in PF3 due to resonance it has got a double bond character. As a result the repulsion between the PF bond is large. It is large, the repulsion, and hence the bond angle is also large. Alright. But there is no case in case of what you can say PH3, we can say that. There is no such case in case of PH3. We don't have anything. Now next point is the dipole moment of carbon monoxide molecule is greater than expected. Whatever we expected, the carbon monoxide molecule, the dipole moment is. Got it? It is generally in case of carbon oxygen, the dipole moment between one carbon oxygen is nothing but 2.25 dBi, so to say. But it is greater than. This is because of the presence of a dative bond or coordinate bond in carbon monoxide. Alright, we are expecting it that, as I said you just now to you, that carbon oxygen. So carbon oxygen means C double bond O. That means it should be 2.25 dBi, but it is not so. Why? Because there is another bond is there, which is a dative bond. Dative bond means coordinate bond between carbon and oxygen. There is another bond is there. Alright, so due to that particular reason, what you find is that when you draw the resonance structure, you might have seen it, that we are having 3 bonds in one case with oxygen. In one case with oxygen, in the resonance structure, in the canonical structure, we have seen the 3 bonds. If you haven't seen, draw it and see. You will find it out. So due to this particular reason, carbon monoxide is having a greater, what you can say, a dipole moment than expected. This is the reason behind it. Alright, why it is more. Now, next is H2O2 molecule has got an open book structure. Now, what do you mean by that? Open book structure means, if you see the structure of H2O2 molecule, the structure is this. That is H2O2. The structure is here oxygen, here it is hydrogen, here it is hydrogen, let us have hmm, we can have it in this way, otherwise if I take it outside, this will go outside. So yeah, this is better. Yeah, this is better. You can see it looks like a book. You can see that. It's an open book structure. We can see that. It's an open book structure. This is called as an open book structure in hydrogen peroxide, where the dipole moment is 2.1 dBi. The dipole moment in hydrogen peroxide is. Alright, if you see the bond angle here, it is 94.8 degree. The bond angle is 94.8 degree. And oxygen is bond length is 147.5 picometer. The oxygen bond length is. Alright, and oxygen hydrogen is 95. Where to write? Let me write here. It is 95 picometer. Oxygen hydrogen is 95 and oxygen is 147.5 picometer, so to say. And this bond angle is this particular bond angle is 111.5 degree. The bond angle is. Alright. So in this way, it is an open book structure. This is said to be as hydrogen peroxide. Alright. So this is the structure of hydrogen peroxide, so to say. That is H2O2. We can say that. Now, the next point is the ability of the hybrid orbitals to overlap in the order. What is that order? sp3 is greater than sp2. It is greater than sp. That is, greater is the p character, greater is the ability to overlap. Alright, that is, again I repeat, the ability of the hybrid orbitals to overlap is in the order sp3 is greater than sp2 is greater than sp. Alright, why? Because greater is a p character, greater is the ability to overlap. Now, greater is a p character means here, see, very simple, you know that. We have calculated the s character and the p character. Here the s character is 25%, so p character is 75%, total is 100. Here S character is 33.3%, P character is double of that, almost 67%, we can say that. Here S character is 50%, P character is also 50%. So 75 or 67, 50, so it is decreasing. So what I said, greater is the P character, greater is the ability to overlap, we can say that. Next, the bond angles formed by the different hybrid orbitals are in the order, got it, are in the order, that is order is going to get changed. That is, here the order will be sp greater than sp2 greater than sp3, because the bond angle here it is 180 degree, here it is 120 degree, it is here it is 109.5 degree. 180 degree, 120 degree, 109.5 degree. All this you know it. So the bond angle formed with the different hybrid orbitals is in this particular order, we can say that. So greater the s character, greater is the bond angle. Why it is so? Because greater the s character, here you see the s character is 50%. S character is 33.3%, S character is 25%. So greater is the S character, greater is the bond angle, greater is the P character, greater is the ability to overlap. Greater is the ability to overlap. So in case of overlapping, it will be reversed. In case of bond angle, this is the, what you can say, the value you got it. Clear? Now, next is, after that, we'll come to, that is isoelectronic species. Now, isoelectronic species, you know, they have got same number of electrons. Not only they have got the same number of electrons, remember it, they have also got the same shape and the same bond order. They have got the same shape as well as the same bond order, we can say that. Isoelectronic species. Now, let me give an example to you. For example, let us take CO2 molecule and azide ion. Azide means N3 minus. CO2 and N3 minus. This is known as azide ion. We can say that. Azide ion. Now, these three have got, what you can say, number of electrons counted. Carbon is 6, oxygen is 8 to the 16. Alright, oxygen has got an atomic number is 8, 8 to the 16, and here carbon is 6. We can say that. So 16 plus 6, we can say how much it is. It is coming to be as nothing but 22. Here N3 minus N3, nitrogen is having 7. 7 3 is 21. 21 plus 1. Alright, so it is 22. So it has got 22 electrons. So these two have got the same number of electrons, we can say that. So in this way, they have got the same number of electrons, we can say that. And hence their shape is what? Their shape is, I said you, the shape is same, linear, as well as the bond order is how much? The bond order is, you can find it is 2. The bond order is nothing but it is 2. The bond order is. Similarly, if you take ozone and O3 and NO2 minus, alright, it has got V shape. These two are again, you find it out and see the electronic number of electrons. That is NO2, yes, NO2 minus. So what you find is that they are isoelectronic species. Got it? They have got the same bond order and they have got the same shape. What is the shape? V shaped. It is V shaped and the bond order is 1.5. The bond order is 1.5 and it is V shaped. We can say that. Similarly, we are having CO3 2 minus. Alright, this one, and also we are having NO3 minus. They are also isoelectronic species. They have got the same number of electrons. You calculate it and see. Alright, so you will find the shape is trigonal planar and the bond order is 1.33. Bond order is 1.33 and it is trigonal planar in nature. We can say that. So in this way, isoelectronic species not only have the same number of electrons in the we can calculate the outermost shell also, the same number of electrons. That also can be done. Got it? We can also do that. Outermost shell, the number of electrons we can calculate. Like here it is outermost shell. If you see, that is 6 electrons is there, isn't it? So 6 2 are 12 and plus 4 16. Carbon is having 4. But better I will say you, if you calculate the total number of electrons, then also it will come the same, as it's up to you. Got it? To do the outermost shell or to do the total number of electrons. Whatever it is, isoelectronic species have got the same number of electrons as well as they have got the same bond order as well as the same shape, we can say that. Now next is there are certain heteroatomic molecules. Heteroatomic means like till now you have done in your regular classes the formation of N2 molecule, O2 molecule, O2 minus, H2 plus, He2, got it? C2, this all. Hetero, this is not hetero molecule. They are hetero, this is not heteroatomic, it is homoatomic. One side oxygen, another side oxygen. O2. On one side nitrogen, another side N minus. So N2 minus. Alright, so both the sides same atoms are involved. So it is homoatomic. Now we can see the heteroatomic molecules. Now heteroatomic molecules like we can have like NO2, we can have NO, we can have CO, we can have, that is nothing but CO3 2 minus. They are all heteroatomic molecules, we can say that. Now in case of heteroatomic molecules, you have to remember certain points. The points are almost similar, but you have to remember some certain things. So what is that? Only atomic orbitals of the same energy can combine effectively. Atomic orbitals of the same energy can combine effectively. In homoatomic also you have read it, that whenever the atomic orbitals are combined, they have got the same energy, understood, for the combination. Now they must have the same symmetry and they must have the same they should overlap to a maximum extent. Alright, they should have the same symmetry. Symmetry means what? Shape. Alright, and they should overlap to a maximum extent. So hence the first point I said, they should have almost the same energy, both the atoms, heteroatoms. Now for example, nitrogen, oxygen, they should have the same energy. Carbon, oxygen, they should have the same energy. Like they should have the same symmetry, same shape, and they should overlap to a maximum extent. Means maximum energy should involved in it. Alright, maximum energy, if it is involved, the minimum energy will be remaining in the compound and the compound will be stable in nature. Now one thing remember that when you are drawing the molecular orbital diagram, so the more electronegative atoms should be towards the bond, bonding molecular orbitals, and the less electronegative atoms should be towards the anti-bonding molecular orbitals. Means I mean to say, that is here we are having, that is this particular one. So here this is anti-bonding will be here. And here this is your bonding molecular orbital, so to say. So this will be, this is your, what you can say, one atom which is less electronegative, we can say that, less En, electronegative, we can say, and this is more electronegative. So more electronegative, let me little bit down, let me do, so that it will be easier for you to understand. Yes, so what you find is that, still properly, yeah. So what you find is that this is your bonding molecular orbital, isn't it? Bonding molecular orbital. So the more electronegative atom will be towards the bonding molecular orbitals, and this particular one is your anti-bonding molecular orbital. So the anti-bonding molecular orbital will be towards the less electronegative atom. Alright, so the less electronegative atom will be towards the anti-bonding molecular orbitals. The less one will be towards the anti-bonding, and the bonding molecular orbitals will be towards the more electronegative atoms, so to say. For example, carbon, oxygen. Carbon will be here and oxygen will be here. I am drawing just now. Here you will not draw. Here you will not write carbon, oxygen. Here you will write the number of electrons. That is 2. Maximum we can write, isn't it? In an orbital. So just I give you an example. So here the carbon will be there and here oxygen. That means this side I will keep carbon and this side I will keep oxygen. That's it. Got it? In case of heteroatomic molecule, this you need to remember. After that, how to find it out? You know that how to find it out. We will write the electronic configuration. Now how to write the electronic configuration? Let me just take an example and tell you the electronic configuration. For example, nitrogen, oxygen. So nitrogen is having 7 electrons, oxygen is having 8 electrons. So 8 plus 7, 15 electrons. So how will I write 15? See here, only directly the electronic configuration of the molecule. Sigma 1 is 2, sigma star 1 is 2. Count it, 4 is there. Then sigma 2 is 2. Alright, sigma star 2 is 2. Clear? So after that, we will come to that is sigma 2p z2, then pi 2p x2 is equal to pi 2p y2. Let us count it and see how much I got it. It should be how much? Nitrogen is 7, oxygen is 8. Atomic number, isn't it? 15 it should be. So here also it should be 15 electrons. 2 plus 2, 4, 4 plus 2, 6, 6 plus 2, 8, 8 plus 2, 10, 10 to 12 to 14. Then after that, sigma star 2p z1. In this way. Alright, so I wrote it in this order. Now I can find the bond order. I can find the bond order. Bond order is NB minus Na by 2. NB is 2 plus 2 4, 4 plus 2 6, 6 plus 2 8, 8 plus 2 10. Na is 2, the star one, 2 plus 2 4, 4 plus 1 5. So 10 minus 5 by 2 it is 2.5. In this way directly we can find it out. We can write the electronic configuration directly. We can also find the bond order directly. In this way you can find it out. We can also say it is paramagnetic or diamagnetic. You can see the outermost subshell is unpaired. Yes, it is unpaired. It is not paired, it is unpaired. So it is paramagnetic in nature. Got it? In this way we can write the electronic configuration directly and we can find out the shape of the molecule. Got it? Shape I am saying. We can find out the bond order, we can find it out. We can find the nature of the molecule, that is magnetic nature. Thank you.